Hi everybody, welcome back. Today we're going to be looking at representations of functions as power series. Now, if you recall from the previous section, we were working with power series, and we started by working on this example in the previous section. Alright, if you haven't watched the video to that section, please go ahead and put pause on this video and then watch that video first, because this one that's going to make more sense if you watch that video first or go through that lesson first. Now, we came up with this conclusion that we were looking at this power series here given by x to the power of n beginning at 0 going towards infinity. And we call this function g of x, and we saw that we were able to get this function representation of 1 divided by 1 minus x for this power series, but only for the convergence for the x values being bounded between -1 and 1. Awesome. So again, we were able to see that last time. Now, we're going to elaborate a little bit more on that. So what I want to do here is I want to now start using this process that we've been looking at to develop a more in-depth version of what's going to happen if, let's say, we were to develop this function as a power series. Well, naturally, from Calc 1, we know how to take derivatives and integrals. Well, look at this power series. It's just term by term. So could we take a derivative term by term, or can we take an integral term by term? Right, the answer to that would be yes, yes we can, and because we can do so, that means we can elaborate more on these power series. Nice. So here's the theorem that we have then. If the power series has a radius of convergence that's greater than 0, the r value, then the function f defined by f of x, and here we have this f of x function being defined as a power series, then that is going to be differentiable on the interval from a minus r to a plus r. And again, a is that center where we're placing our convergence at, and r is that radius of convergence. And we're going to get two things to occur. Number one, the first thing that we get to occur is that we can take the derivative of the function that we know how to do from Calc 1 and a little bit from Calc 2, but more importantly, we will be able to use that differentiation process on each individual term that we are observing for on the power series. Therefore, when we take the derivative of the power series, notice that all we're doing is using this process, which was known as your power rule. Part 2 says that we can integrate this function f of x dx, but that means integrating this whole function means that we're going to be integrating each individual term by term for the initial power series. And we have to be very careful here, simply because when we do term by term integration, that's very nice, but we oftentimes, every time we do an indefinite integral, we oftentimes get this constant of integration, and we must always account for that constant of integration. Alright, so again, we're working with the exact same process, but now again we're wanting to apply more calculus to this, more derivatives, integrals, and stuff like that. But again, anytime that we figure out, hey, can we express this function as a power series? Well, that power series we then need to figure out, is it always going to model it? Is it going to model it sometimes? And for that we need to talk about convergence, right? Is it going to converge on an interval? Is it going to converge everywhere? Or does it not converge at all? Alright, so what we're going to do is we're going to work on a few examples just to kind of get our feet wet to go through this whole process. Alright, so here we are. Here's the examples that we're going to be working on, or the example. Find a power series representation for the function and determine the interval of convergence. Alright, so we now have to find a power series representation for this function, and we're going to determine that interval of convergence. Alright, so again, there's a few things that we're going to have to do here that we're first going to have to start analyzing. All right, number one, we need to figure out what this function overall looks like. And for that, I'll just go ahead and I'll rely on the fact that we're going to have this one function that we automatically know. So what I'm going to do here is I'm going to start by saying, well, this kind of looks like, I'm just going to say here in green, looks like 1 over 1 minus x. So it has that resemblance. The only difference is that this denominator doesn't have a 1 minus x, it has 1 minus 4x squared, which means I then need to go ahead and make a few adjustments for that. All right, so this is going to be the adjustment that I'm going to make then. All right, so I'm going to be using this function, which is right up here, that I'm going to call g of x. All right, so I'm going to be looking at g of x, which is this 1 over 1 minus x. All right, and I'll make some manipulations as we go through. All right, so in here, this is the summation as n begins at 0 and tends to infinity, and this is going to be for x to the power of n. Now, if you go back and if you look at it, yeah, it's the exact same one. All right, so good. Now, I'm going to say that this equality only holds for the x values that are bounded between -1 and 1. Awesome. Now, let's start making some of these manipulations then. Well, the manipulations that I want now is I want to change this x value. I no longer want it to be this x value. I now want it to be 4x squared. So when I do this, I got to now think about what does that change, right? So essentially what I'm doing is I'm taking this g of x function, and instead of the x value, what I'm doing is I'm inserting 4x squared into each individual component. So what that gives me now is 1 minus this quantity here, which is my 4x squared, just like such, is equal to the summation beginning at n is equal to 0. Again, I substituted my x value, so this now becomes 4x squared raised to the power of n. And again, this still only holds for the x values being between -1 and 1. All right, nice. So once we have this, we can now go through and we can now start modifying. Oops, I'm sorry, not for those values. My apologies. This only works for the values of my initial substitution, which was 4x squared. There we are. Okay, let's keep going. So we now have this representation here, and this representation, this is now my f of x. And again, because I'm looking at this, or sorry, I'm going to multiply by 5, that way I can now get it to become my f of x. So in this particular case, f of x is equal to 5 times g of 4x squared, which then becomes 5 divided by 1 minus 4x squared, which is equal to 5 times the summation of n is equal to 0, and that's 4x squared multiplied, or sorry, to the power of n. And again, this only holds for -1 being less than 4x squared being less than 1. Nice. So everything looks good so far. That's great. So my interval for convergence is this interval right in here. So this told me to find a power series representation, and I did. This is my power series representation for that function, and then determine the interval of convergence. All right, well, I still have to determine that interval of convergence, so let's go ahead and let's find that now. So now that I have this summation, this is what I need right here. All right, so I'll just keep that in my back pocket. All right, that's one of the first parts. Now, I need to work on this interval for convergence. All right, so let's do a little bit more work there. All right, so what I'm going to do is I'm going to divide by 4 here. All right, so let's go ahead and let's divide by 4. There we are. Oops, excuse me. 1 over 4. Perfect. All right, looking good so far. Now, what I'm going to do here is I'm going to take the square root. Now, the only reason I can take the square root at this point in time is because I have this compound inequality, and this compound inequality is in fact in the way that I need it to be. All right. So when I want to take the square root, there's going to be an issue. Somebody's going to say, hey, Mr. Castro, there's a negative right over here. And you're absolutely right. There is a negative here, and we need to somehow, some way bypass that negative. Right? So one of the things that I'm going to do here is I'm just going to come really quickly, and I'm going to rewrite this slightly different. I'm going to rewrite this just like this. All right? Looking good so far? Hope so. Now follow me on this and see if we can come to a conclusion here. I can do this. Oops. There we are. Just like that. Still works. Good. Can I take square roots? Sure I can. Now, the issue with the square root, that when I take this, I get a plus or minus. All right, now when I do the plus or minus, I just have to be careful here because I do get a plus or minus, and when I do this, I'll essentially be looking at the interval. Oops, I left a absolute value here. I will be looking at the interval that is bounded, or that bounds x between negative a half and a half, which means this is my radius of convergence. So my radius of convergence here is 1/2. What about the interval? Well, my interval here for convergence is negative 1/2 to 1/2. Interval of convergence. But again, this is so far. So we have to check the endpoints, right? So let's go through and check the endpoints when x is equal 1/2 and then when x is equal to negative 1/2, and we're going to see what happens. All right, so I'm going to use x is equal to negative 1/2, and I'm going to see what happens here when I substitute it into my formula here. So using f of x, I'm going to use f of 1/2 here. So this is going to be 5 multiplied by the summation of n beginning at 0, and this is 4 times my x value here of negative 1/2. So this is going to be negative 1/2 squared, like such, and all of that raised to the power of n. Alright, looking good. N is equal to 0. And then this is now in here going to get me just 1, so this is just going to get me 1 to the power of n. Alright, now because negative 1/2 to the power of 2 gets us 1/4, 1/4 times 4 gets us 1, so it just ultimately becomes 1 to the power of n, which means at this point in time we just get a constant function, which means this will, at this point in time, I see it as converging. My apologies, I said converging, but it means diverging, because as it goes to infinity, we're just going to keep adding a whole bunch of 5s as we proceed through the whole process. So this is going to be diverging. And notice, because of the square in here, the same thing is going to happen again if we use the positive version. So if I go through and if I use x is equal to 1/2, then naturally I'm going to get the exact same values out, which means ultimately this function at the endpoints will always diverge. All right, now let's clean this up just a little bit. There we go. So let's make that positive half. So if x is equal to 1/2, and then here we get 4 times 1/2, there we go. Then we still get 1, and again, this is still going to diverge. So the endpoints for this interval is still correct. So the power series representation for, what is that, 5 over 1 minus 4x squared is this summation and beginning at 0, and then where is it at? Right in here. This is 5 times 4x squared raised to the power of n. I'm going to say the radius of convergence is r is equal to 1/2, and the interval of convergence is -1/2 to 1/2. Open parentheses on both of those values. So there we are. That is what we are essentially looking at. All right, and that is how we are going to be looking at these specific values. So let's go through and let's start looking at another example that's going to look fairly similar to this. All right, so let's look at the next one. Let's look at part B. Oops, sorry. So for part B, what I'm going to be looking at is I'm going to be looking at my function, call this f of x, which is going to be equal to x divided by 5 minus x. All right, so our overall goal is to, once again, kind of get back to this original function that we wanted to see, that 1 over 1 minus x. So again, this kind of looks like 1 over 1 minus x. So all we have to do then is kind of get it into that form. All right, so what I'm going to do is I'm going to start manipulating this function to try to get it into that form. All right, so I'm going to first of all separate my numerator from my denominator. So if I separate my numerator from my denominator, this now gets me what I'm looking at here. All right, not too bad. All right, so what I'm going to do now, since I have 1 minus x, I kind of want a 1 right here. So what I'm going to do is I'm going to factor out a 1/5. And let's see if I can get that going here. So f of x is going to be equal to, and I'm going to say here, this is going to be x over 5 multiplied by 1 over, and this is going to be 1 minus x over 5. Now you can double check. If we multiply this 5 into that denominator, we get 5 minus 5 times this would just be 5 minus x. So we're kind of good on that front. Now that we have this initial piece, the 1 divided by 1 minus x divided by 5, I kind of want to go through and modify this at this point in time. All right, so I want to now incorporate my sigma notation here. All right, and the way I'm going to incorporate my sigma notation there is by looking at this function here. So if we have this 1 over 1 minus x to be equal to the sigma notation for n is equal to 0 of x to the power of n, when I insert my x over 5 as such, this is now going to change this input to be x over 5 to the power of n. And that's actually what I'm using here. So when I do this, when I say, hey, my f of x is now your x over 5 multiplied by sigma notation here, n is equal to 0, and I'm going to take these values for x divided by 5 raised to the power of n. All right, that's not too bad, but again, at the same time, this only works for your argument that x over 5 being less than 1 and greater than -1. In other words, the absolute value of x divided by 5 must be less than 1. All right, not too bad. So let's go through and let's extract this interval of convergence, or this radius of convergence that we need, which means this in here will be the absolute value of x less than 5. All right, not bad. So that's actually pretty good for what we need. All right, this gives us my radius of convergence. So my radius of convergence in this particular case is just going to be 5. Not too bad. All right, now interval of convergence. Let's go through and let's start analyzing that interval of convergence. It's actually given to us here, which is actually really nice. All right, so the interval of convergence is, and again, we can double check the endpoints is -5 to 5. But again, the endpoints we could check with 5 and -5. Remember, 5 and -5 in here, if it's 5, it just becomes 1. If it's -5, then this becomes -1 to the power of n. It becomes an alternating series. Alternating series doesn't have this convergence as you're looking at the limit, therefore divergence test will cause it to diverge. So if it's 1, then that means this endpoint is going to diverge. If it's -5, then that means it's going to be -1, and that means it's going to be an alternating, does not converge. So again, open endpoints for what we need. That's kind of nice. So again, just by looking at this, we have all these representations that we're getting, which is super good. All right. So the interval of convergence is from -5 to 5, and the radius of convergence is r is equal to 5, right? R is equal to 5, then the radius of, interval of convergence is -5 to 5. Now, the power series representation. Check out what I'm going to do here. I'm going to modify this just a little bit more. I'm going to say this is just f of x, and remember, this summation, this power series, only values, or the only values that change are n's, which means x divided by 5 is a constant, so it can move through this sigma notation to multiply these values, which means we're going to get x multiplied by x to the power of n divided by 5 times 5 to the power of n. What does that mean for our geometric representation, or for this power series representation? This means that the power series representation for x divided by 5 minus x is going to be equal to the summation, n beginning at 0, for x to the power of n plus 1 divided by 5 to the power of n plus 1. And there you go. Right? It doesn't look too bad when we start looking at it, but again, we have to go through the whole process and the whole argument to figure out what is going to be those convergence values. Now, there is one important topic that I kind of glanced over, and I really didn't discuss it at this point in time, but notice, when I was talking about radius for convergence, or these values that x over 5 is going to be converging for, lesson 1, what's happening here is that, look at these values, the x over 5. I didn't consider x over 5 because, again, at the end of the day, this doesn't really add anything to my radius of convergence or this interval of convergence. The only item that it really adds to is just the overall terms that we're looking at. But again, the radius of convergence only depends on what's changing with your n values. Because x and 5 out here, these are constants, these do not affect that radius of convergence. So therefore, we only need to focus on the power series that will cause that radius of convergence. All right, awesome. Looking pretty good so far. All right, now, what we're going to do now is we're going to start trying to identify these power series representations, or these values that we're going to be looking at for these integrals or these derivatives for these functions. All right, so here goes an example that we want to work on. All right, so we want to find a power series representation for let's call this g of x, is equal to 1 over 1 minus x to the power of 2. There we are. And determine its radius of convergence. All right, so here we go. All right, so we got a lot to do here. All right, we got a lot to do here, and there's going to be a lot of work that we're going to need to dissect in order for us to be able to extract what it is that we have here. All right, so notice these values, this g of x function, what I'm going to do here is I'm just going to write g of x is equal to 1 over 1 minus x quantity squared. There we are. And I'm going to say this kind of looks like one over 1 minus x. And again, we always try to go to something that we know what it looks like. And in this particular case, 1 over 1 minus x kind of looks like almost everything here. So one of the items that I want you to then see is, okay, well, we do have that it kind of looks like that, but there's only one issue, is that this has a square. So we need to try to somehow, some way undo that square. And we're not going to be able to undo it by taking a square root, because we can't apply the square root to both sides. So that's not a possibility. However, if you identify that this here kind of resembles taking the derivative of 1 minus x. And we could run through really quickly to just double check, make sure that that is what we're looking at. So if I have some function, and in this case I'm going to say, let's call it f of x. If I have f of x to be 1 over 1 minus x, then this naturally is 1 minus x to the power of negative 1. Taking the derivative here, take the derivative here, drop the exponent forward. So drop the exponent forward and we get 1 minus x, subtract 1 from the exponent, and then multiply by the derivative of the inside. The derivative of the inside is just negative 1, which means negative times a negative gets us a positive, which means we're only left with 1 minus x to the power of negative 2, which is 1 over 1 minus x quantity squared, which is this function g of x that we're looking at. So if we're given this function, how can we get back to this one? Well, we then have to find its antiderivative, and that's exactly what we're kind of looking at here. We're saying, hey, we took this function, but in order to get here, we had to take a derivative. All right, so keeping that in our back pocket now, we have more tools at our disposal. So now what I want to do then is I want to now keep working with this function here that I just found. So look at this function here, the function of 1 divided by 1 minus x. This is your power series where x is just to the power of n, just like this. But again, this only works for the radius of convergence where x is equal to 1. Or sorry, where x, the absolute value of x is less than 1. All right, not too bad. All I have to do then is just start looking at this individual piece, right? I need to take this derivative term by term, but knowing the properties of derivatives and how they work, we could just take the derivative of x to the power of n. All right, that's not bad. So what's the derivative of x to the power of n? Well, that drop the exponent forward, that's just n, multiplied by x to the power of n, subtract 1 from the exponent. There we are. All right, and again, this only works for the absolute value of x is less than 1. Nice. So, find a power series representation. Guess what we just did? This is your g of x. this is g of x, right? Following that whole equality, we found g of x. G of x is this 1 divided by 1 minus x quantity squared, and it turns out that's this actual power series, which again only works for the exact same radius of convergence for the initial power series of x to the power of n. Awesome. So it kind of looks like it's working very, very similar to what we were doing before, with the only added difference now that we're using derivatives or maybe integrals. So the question did also say determine the radius of convergence, and the radius of convergence is still going to hold the exact same. So the radius of convergence for g of x, which is 1 over 1 minus x squared, which is the summation beginning at 0 for n times x to the power of n minus 1. Oh, I'm sorry. I used n is equal to 0, and it's actually n is equal to 1, because when we re-index and when we take the derivative, the first constant becomes a 0, and therefore we're left with n is equal to 1. My apologies. There we are. And so all of this, x to the power of 1, is negative 1 to 1. There we are. Oh, sorry. I meant radius of convergence. Cheese and crackers. My apologies, guys. So the radius of convergence is 1. There we go. And the interval of convergence is from negative 1 to 1. There we are. Perfect. Awesome. Right on the money. All right. It's looking pretty good, guys. It's looking pretty good. So let's look at a different example then. All right. A different example which is still going to be somewhat similar to this, but again, we want to find those power series representations. So let's go with this example here. So we want to find a power series representation for, we're going to call this h of x, which is going to be the natural log of 5 minus x. And we're going to determine its radius of convergence. All right, so having this power series, or we need to find a power series representation for this natural log of 5 minus x. All right, so we need to go through that whole process. So what I'm going to do here is I'm just going to say, hey, I'm looking at h of x in this particular case. So h of x, here we are. And h of x is the natural log of 5 minus x. Now, again, what I said at the very beginning is that we always want to make sure that this looks like that one initial power series of 1 divided by 1 minus x. So we need to try to get there. All right, but as it stands, it doesn't kind of look like it's there. So we need to develop some process for it to make sure we get there. All right, so one of the things that I'm going to allow you, or one of the things that you need to then recall, is that when we take the derivative of, let's say, natural log of x, the derivative of natural log of x is just 1 over x. Okay, that's not too bad. So what then if we take the derivative of natural log of 5 minus x? Well, if we take this derivative then, natural log, this is going to get me 1 over 5 minus x multiplied by the derivative of the inside, which is just negative 1, which means it gets me negative 1 over 5 minus x. Hey, that kind of looks familiar. this kind of looks familiar because now this is kind of that form of that 1 divided by 1 minus x. Slightly different, but it's still what we need. All right, so it is what we need and it is what we're looking for. So let's go back to this process over here. Natural log of 5 minus x. That's natural log of 5 minus x. Well, how do I undo a derivative to make sure I get to this function? Well, the way we undo a derivative is by taking an antiderivative. So what I want to do at this point in time is I want to start by then taking some antiderivative and seeing where that's gonna kind of lead me to, seeing where that's going to kind of lead me into. All right, so here we go. Now remember, there's a free-floating negative over here, so I want to make sure that my initial natural log does not have a negative, so I'm going to make sure I incorporate that into my antiderivative over here. So I'm going to have my antiderivative here for this function for negative 1 over 5 minus x, and this is going to be dx. All right, because again, I'm looking at this bridge here, this derivative that I took. The derivative for that function is the function that I want to look at. All right, not too bad. Now, negative moves outside that integral, so that's not too bad. So negative moves right outside, and I'm now left with 1 over 5 minus x, and this is going to be dx. All right, that looks pretty good, and that should actually remind you of the function that we were working with on this very first problem here, right? Minus the x value. So if you take away that x value, then it's exactly that function that we're looking at, which means we're still going to be able to apply that same process. So in here, I'm going to have this negative for this integral, and then I'm going to have this summation, and that's this piece in here, n beginning at 0 for x to the power of n divided by 5 to the power of n plus 1, and this is all with respect to dx. Now again, when or how does this work then? Well, if you remember, we're going to have our interval of convergence, and this is going to be only works for the absolute value of x is less than 5. And again, just to double check, we go through, and what we were looking at here says that our interval of convergence was the absolute value of x is less than 5. And that's what we're using for this individual piece here. All right. So, looking good so far, hopefully. Let's go through and let's keep on doing this whole process. Now, when we start doing the integration, so the integration techniques that are going to take place here, when we integrate, we're going to need our constant of integration plus, or in this case minus, because I have the minus here, minus, and now what I need to go through is I need to integrate these individual values here. So integral of the summation, and this is going to be term by term. Now if it's done term by term, then that means this is just the integral for x to the power of n divided by 5 to the power of n plus 1, and this is dx. So it is done term by term, but it's only done for the x's, which means the x values are the ones being integrated. So that's going to tell us that for the numerator, we're just going to get x to the power of n plus 1. The denominator is going to be n plus 1 multiplied by 5 to the power of n plus 1. All right, not bad. So this is what we're looking at here. And again, this is all the h of x value that we are initially observing. All right, not too bad. So let's see if we can try to solve for that constant of integration. All right, so right here in green, I'm going to say try to solve for c. Chances are with a lot of these problems, you will be able to solve for c. So if we solve for the constant of integration, that means I must choose an x value. Well, what can we choose as our x value? So I'm going to say try x is equal to 0. So if x is equal to 0, that's going to leave me with h of 0, which is the natural log, using my initial function, of 5 which is my constant minus the summation and beginning at 0. Remember, I chose x is equal to 0. That means my numerator here is 0. So numerator doesn't matter what the denominator is, because at this point in time it's all 0. So we naturally then get that my constant of integration here is just the natural log of 5. Wow, that's awesome. So now, when we have a power series representation, so the power series representation for the natural log of 5 minus x is equal to my summation, or sorry, in this case my constant that I just found, which is the natural log of 5, minus the summation of n beginning at 0, and this is going to be for x to the power of n plus 1, divided by n plus 1 times 5 to the power of n plus 1. Awesome. The radius of convergence, we already have that from up here. So the radius of convergence is r is equal to 5, and the interval of convergence is -5 to 5. And there we are. And that is the representation for functions as power series that we use in this particular section. Awesome. So that now wraps it up for this section as well. So again, the overall goal is you always want to try to get to somewhere along the lines of 1 divided by 1 minus x. Somewhere, some way, try to get there. All right, using derivatives, using algebraic manipulation, or using integrals, try and get there. All right, so I hope you all enjoyed this lesson, and I will see you all for the next one.